This is the software architecture map of my CubeSat project. By the end of this video, you will understand how all of this fits together and how I plan to operate my satellite. Satellites usually get attention for their hardware, the solar panels, the thrusters, the radios and the sensors. But just like a smartphone, it's the software that makes everything work together. Here is an artistic rendering of my CubeSat orbiting Earth, hopefully a few years from now. Internally, the CubeSat is a distributed computer system made of 4 boards: power, avionics, sensors, and communication. And when it links to the ground station, it becomes an even larger distributed system. This architecture is what enables the entire mission. The most basic level, each board runs a classical Superloop pattern. A setup phase that initializes everything, a loop that repeats the same steps over and over again. Inside that loop, we run tasks for command, control, and housekeeping. This creates a cooperative task scheduler, extremely fast and low overhead if each task either finishes quickly or yields instead of waiting or pulling. There is no preemptive scheduler. If a task blocks, nothing can take the CPU away from it. So tasks should not call device functions directly. Instead, tasks interact only with buffers and queues, while interrupt handlers and direct memory access move data to and from the hardware. This avoids waiting, avoids polling, and keeps the CPU free. The price of that is memory management, which must be thread-safe or preferably static. By now you have seen the color coding: green for setup, blue for Superloop, purple for hardware access with interrupts and direct memory access. Let's look at the task for command, control, and housekeeping. Each task runs once per Superloop iteration. Tasks live in the application layer and communicate through the transport layer using OpenCyphal. OpenCyphal supports CAN, serial, and Ethernet transport. I've wrapped all 3 libraries into a unified interface that I call CommonCyphal, so tasks can publish and receive messages without caring about the underlying transport mechanism. Each transport library has handlers that push and pull data from buffers. Interrupts and direct memory access shuttle data between hardware and buffers. On send, the physical interface interrupts when idle, and the direct memory access moves data from buffer to hardware. On receive, the interface interrupts and moves data into buffers. Once per Superloop cycle, the reception buffers are drained into OpenCyphal, which reassembles frames into messages and places them onto message buffers. The loop processor assigns messages from the message buffer to tasks, but how does it know which task wants which message? During setup, tasks register their message interest with the registry. The loop processor can now distribute incoming messages based on these registrations. Tasks that receive messages have a small message buffer where the loop processor places them. To limit incoming traffic, OpenCyphal filters frames based on subscription, again informed by the registry. Messages can also be re-injected into transport libraries to route between buses. This relay allows to exchange messages between the CubeSat boards and the ground station. However, not all messages go between nodes, some stay on the same board. For that, I created a loopback library which follows the same traffic pattern. It is also extremely useful for testing because it's hardware independent. Tasks are the workhorses of the system. They can be customized with mixin. Let's focus on tasks for a few slides. Trivial tasks define a handle task method and use interval and last tick to determine when to execute next. Examples include blinking an LED as a health check or logging memory usage. The publisher mixin adds in the ability to publish messages, for example to broadcast a heartbeat or the current attitude. The receiver mixin adds the ability to receive messages. It has a message buffer and tells the registry which messages the task wants, for example, the current location. A more specialized communication pattern is based on designated clients and servers. The server waits for a request from the client, then responds. An example is writing a file to the server. Its counterpart is the client task, which sends a request to the server and waits for its response. Clients and servers must implement state machines to yield while waiting, which provides a hook for flow control, acknowledgements, and timeout. Additional mixins like pacer or trigger allow further specialization. The pacer is mostly dormant, but periodically hyperactive. The trigger executes only when a specific condition is met. Combined, they can be used to form a photography task that sleeps until the satellite flies over the target region, then takes a burst of photographs. As promised, we have now walked through the entire architecture diagram and explained every box. One major benefit of this architecture is that the entire software stack can be made testable under Linux. This dramatically reduces development cycle time, debugging is easier, faster, and safer than on an embedded hardware system. But unit and integration tests deserve their own video. All the code is available on my GitHub repository. Thanks for watching, see you next week.